Hey everyone, just following up from lab today with a couple of things to go over, some calculations and some hints and some tricks. So what we did was we did two chemical reactions and we monitored the temperature within a coffee cup calorimeter. And the first one we did was citric acid and sodium bicarbonate or baking soda. And our temperature, our final temperature actually was lower than our initial temperature, if you can recall. And in the second experiment, we mixed hydrochloric acid and sodium hydroxide, and our temperature curve looks something like that, where our final temperature was actually higher than our initial temperature. So for the first experiment, if you were to calculate a delta T, that's final minus initial, that would be a negative value. So a negative value. This one here in the second experiment, delta T would, of course, because TF is higher than TI, would be a positive value. So I want to go through and lead you through the calculations with one of these solutions, and then you can do the other one on your own. Let's pick the first solution and chemical reaction we did, which was citric acid and sodium bicarbonate. And what ultimately we want to do is figure out the delta H of reaction. And this value will be in kilojoules per mole of reactant. And for the first experiment, it tells you to actually calculate the number of moles of sodium bicarbonate that you used. So that's going to be moles of sodium bicarbonate. This is kilojoules. Excuse my little j there. And so we're going to try to find the heat of that reaction, the top part here. Which is a little confusing to some. So what we need to do is recognize that the heat of the reaction is really the heat, little q, of the reaction divided by the number of moles. We'll get to that part later. This is the weird part here, this heat of reaction. For a coffee cup calorimeter, what we do is we look at the heat of the solution, and then that is equal to the heat of the reaction, except with the negative sign here, or it's the same magnitude, but just you got to invert the sign. So let's go through that with our first experiment with our citric acid and our sodium bicarbonate. We're going to calculate Q of the solution, and that is equal to the mass of the solution times the specific heat of the solution times the temperature change. Okay. The mass of your solution, well, you used 100 milliliters of citric acid. You can assume the density is 1 gram per mil. So now I have that equal to, well, that was 100 grams. But don't forget that you added sodium bicarbonate to it, and that was 3.5 grams. So your total mass here of your solution, write it down here, is 103.5 grams. Great. Multiply that by the specific heat of the solution. That is the specific heat capacity of water. We can make that assumption. Our solutions were mostly water. These were dilute solutions. So that is joules per gram degree C. Notice that grams will eventually cancel out. I'm going to multiply that by the temperature change. Temperature change is the final temperature minus the initial temperature. And for our first experiment, you notice that the final temperature was lower than your initial temperature. Okay, so that would be a negative value right there. I'm going to just make up a value and say, back here, that was a delta T, that was negative 2 degrees Celsius. Your value will be around that. So I'm going to call that my delta T, and we're going to call that negative 2 degrees Celsius. Okay? So here we have the equation with all the values. If I did my calculations right, Q solution in my little instance here will come out to negative 865 joules. Why negative sign? Because that delta T was driving that negative component of it. All right, so my heat of solution is negative, but here's what I have to remember. Go back up to this. I really want my Q of my reaction, so I can divide that by the number of moles and get my final answer. But in order to do that, I need this Q reaction, remember Q solution, which is negative 865 joules, actually equals the negative of Q reaction. What does that mean? I'm just going to change the sign here. Q of my reaction will now equal positive 865 joules. All right. I'm almost there. I have Q reaction. What I'm going to do with that is go way back up here, divide that by the number of moles of my sodium bicarbonate, and make sure that eventually gets into kilojoules per mole. And that's where I can end. So a lot of calculations here, but I think the really tricky part was you are monitoring the heat of the solution. It's kind of like a surrogate way, a backdoor way of getting to the heat of the reaction. You have to do a sign flip there. Because our Q solution in this instant was negative, Q reaction, the heat of the reaction, ends up being positive. That will tell you that ultimately your delta H is also a positive value. What does that tell you? It tells you it was an endothermic reaction, one that absorbed heat from the surroundings. Okay? In the other instance, you'll notice that your delta T will be positive. You'll have a Q solution that's positive, but your Q reaction will end up negative. So when you mix an acid and a base, as we did for the second experiment, your delta T is positive. Your Q solution will be positive. Your Q of your reaction will be negative. Exothermic reaction, giving off heat. I'm going to add 2 little videos that you can take a look at. I didn't create them, somebody else did. Hopefully we'll help you with these calculations as well if you're having difficulties. I hope this helped. Bye.